Okay, welcome to Exam 3 Review for Chemistry, for General Chemistry. Okay, we're doing Chapter 5 and Chapter 6 for the exam, and this is Chapter 5 for gases, inert gases. So at 46 degrees, the sample of ammonia gas exerts a pressure of 5.3 atmosphere. What is the pressure when the volume of gas is reduced to 1/10 of the original volume at the same temperature? Okay, so we're comparing P1, V1, and remember PervNerd is our equation, but we're changing the pressure. So basically, these are all held constant. And then P2, V2 is held at a constant. And this is the same constant, so we can set P1, V1 equals to P2, V2. And then so this is our equation, and you get a point for the equation. And then what is the pressure? So we're solving for P2. So we need to isolate our variable, P2. It's connected to the volume by multiplication, so the opposite of that would be to divide both sides. So that's P1, V1 divided by V2. And there's another point that you get for isolating your variable. And then another point is defining these parameters. So the temperature is constant at 46 degrees Celsius, exerts a pressure, P1 equals 5.3 atmospheres. What is the pressure? So what's P2? When the volume of the gas, V1 and V2, is reduced. Okay, so reduced. So what I do when I see like 1/10 or a half, I just go ahead and set that V1 to 1 liter. And then V2, if it's 1/10, it'd be 0.10 liters. Because I like to work with real numbers. So now I can plug and chug into the equation. So P1 is 53 atmospheres, or I'm sorry, 5.3 atmospheres. Keep your units to make sure they cancel out so you know you're doing it correctly. 1 liter divided by 0.10 liters, and solve for P2. So if you put this in your calculator, you should get 53 atmospheres. As the liters cancel out, you're left with atmospheres, and that is P2. Okay, the next problem says a sample of air occupies 3.8 liters when the pressure is 1.2 atmospheres. So let's just go ahead and P1 is 1.2 atmospheres and V1 is 3.8 liters. Now it says what volume does it occupy at 6.6 atmospheres? So P2 now is increased to 6.6 atmospheres, and it's asking for what is the volume, the new volume. So our formula, PV equals nRT, like I said, this is equal to a constant, so then you can go P1 V1 equals P2 V2. You're solving for V2, so that's worth a point right here. This is worth a point when you define your parameters. And then another point is isolating your variable, P1 divided by P2 times V2. And then solve for V2. So 1.2 atmospheres, make sure you keep your units, divided by 6.6 atmospheres. And V2, that should be V1 right there. V1 is 3.8 liters. And then when you divide 1.2 by 6.6 times 3.8, V2 should work out to be 0.69 liters. And you're dealing with two significant figures. Okay, so part B, what is the pressure, what pressure is required? So now we're solving for P2 in order to compress the gas, so V2 to 0.075 liters. The temperature is kept constant. So you're using the same formula, P1 V1 equals P2 V2. This time you're solving for P2, so P2 equals P1 times V1 over V2. And then you put in your new variables, which would be 1.2 atmospheres times 3.8 liters divided by 0.075 liters, and that equals P2. Your liters cancel out to give you 61 atmospheres. And that is your answer. All right, so we have a 36.4 liter volume of methane gas is heated. So we're changing temperature, and this time we're at constant pressure. So P1 V1 equals nRT. We're at constant pressure. And what is the final volume of the gas? And we're changing the temperature. So these are the constants. So then you get these on the same side of the equation. V1 divided by V1 divided by V2 equals V2 divided by T2, and it wants to know what the final volume is. So we're asking to solve to isolate V2. So V2 is connected by T2 by division, so the opposite of that would be multiplication of both sides. So you end up getting V1 times T2 divided by T1. And then when you define your variables, which is worth another point, you have V1 equals 36.4 liters. And okay, so from would be T1 of 25 degrees Celsius. 2 would be T2 of 88 degrees Celsius. And remember, we're not doing heat capacity and chapter 6 enthalpy and heat calculation. So we're doing the gas laws. And when you're dealing with the gas laws, you're going to have to convert this to Kelvin. So remember to convert to Kelvin. And you do that by adding 273 Kelvin to each one of these numbers. And that's going to be 361 Kelvin. And the, actually, backwards. This one's going to be 298 Kelvin, and this one's going to be 361 Kelvin. So now when we put this in the equation, V1, 36.4 liters times 361 Kelvin divided by 298 Kelvin, the Kelvins cancel out, and V2 equals 44.1 liters. And if you wanted to take two significant figures because of the temperature, it would be 44 liters equals V2. Okay, the next question. Calculate the number of moles of gas present. Okay, so we're only given one condition, so this is PV equals nRT. That's worth a point. And let's go ahead and define our variables. So volume is 2.3 liters. Temperature is 32 degrees Celsius, but we're going to convert that to Kelvin. So that will be 305 Kelvin. Pressure is 4.7 atmospheres. And we need to calculate moles. R is the gas constant of 0.08206 liters times atmospheres divided by mole Kelvin. So we make sure that every variable is in terms of this gas constant, and it is. And since we're solving for the number of moles, we're going to rearrange this equation to isolate our n variable, and n is connected to RT by multiplication, so the opposite of that is to divide both sides. So this is be PV divided by RT, and then if we plug in our variables, we see that we have 4.7 atmospheres times 2.3 liters divided by 0.08206 liters atmospheres mole Kelvin, and the temperature then would be 305 Kelvin. Make sure you keep your units if you want full credit, and liters and kelvins cancel out to give us moles. And just double checking all my maths here. N would then equal 0.43 mole. This problem, we have to calculate the density of gas in grams per liter. So what do we know about density? Density is grams. Okay, so grams divided by volume. In this case, we have liters, which is usually use liters for gas. When you're working with reagents in the laboratory, a lot of times that's grams per milliliter, but just mass over volume. Remember here. Okay, so here's density. See my broken heart? There's mass over volume. So there's the volume, and there's the mass. Okay, so we have gram, which is a unit of volume. Okay, so we need to find the density, and since density is grams over liters and we're given grams of 4.65 grams, and we're given a volume of 2.10 liter vessel. So, okay, so then we're going to solve for density. So 4.65 divided by 2.10 grams over liter should give you a density of 2.214 grams per liter. Now, that's A. B is, what is the molar mass of the gas? So we have a formula we have memorized. Molar mass, which is this cursive M, is dirty P, remember? dRT over P. So D is the density, and it's already in terms of molar mass, so we don't have to isolate our variable. We just need to fill in density is 2.214 grams per liter. R is 0.08206 liters atmospheres divided by mole Kelvin. T here, you have to have it in Kelvin, so 27.0 degrees Celsius plus 273 Kelvin equals 300 Kelvin. And then the pressure is given to us, and it's 1.00 atmospheres. So when we solve for the molar mass, we put in 2.214 grams per liter times 0.08206 liters atmosphere mole Kelvin and 300 K, all divided by 1.00 atmospheres. Our molar mass then ends up being 54.5 grams per mole. And that is B. Okay, this problem says at STP. Well, anytime you have STP, you have to memorize what is that. And that would be the temperature at 273 Kelvin and the pressure at 1.00 atmosphere. And I have told you in class, whenever you see STP, you know that 22.4 liters equals 1 mole of gas. And you go ahead and write that conversion factor down because it might make your life easier for solving the problem. Okay, so you have 0.280 liters of gas weighs 0.4 grams. Calculate the molar mass. Okay, so what is molar mass? Molar mass is grams over mole. So as we see, we have grams. Grams equals 0.400 grams. We're solving for the molar mass. We have liters. But we also have this conversion that can convert liters to moles. So we can go from liters to mole of gas. And we need mole of gas for the bottom of that equation. So we can do 0.280 liters over 1. 22.4 liters equals 1 mole of gas. And that works out to be 0.0125 mole. And then we can solve for molar mass by taking 0.400 grams divided by 0.0125 mole, and that works out to be 32 grams per mole. Okay, this problem is asking about the molecular formula. So the molecular formula is the actual formula. Okay, so our goal, one of our formulas, we have to take the formula mass, the molecular weight of our molecular formula at the end, and we're going to have to divide that by the molecular weight of the empirical formula. And that is going to give us a number, and that number we can multiply the subscripts of our empirical formula by. So right now we have CH as our empirical formula. All right, empirical formula equals CH. And since there's nothing there for your subscripts, those are 1. And we're going to find this number to multiply that through, and that's how we're going to get our molecular formula. So what do we need to do in order to get our molecular formula? Well, we know that molecular formula is grams over mole. And we are given grams equals 0.145 grams right here of this compound. We need moles. Notice we're given a temperature of 200 degrees Celsius. We're given a pressure of 0.74 atmospheres, and we're given a volume of 97.2 milliliters. And this is a gas, and we can do PV equals nRT, and we can solve for N. So N equals PV over RT. So R would be 0.08206 liters atmosphere mole Kelvin. We can't use milliliters here. So if we convert this to liters, then this would be 0.0972 liters. We can't use 200 degrees. We have to convert this to Kelvin. So if we add 273 Kelvin onto that, we get 473 Kelvin. So now we can plug into our equation. Our pressure is 0.74 atmospheres. Our volume is 0.0972 liters. Our R is 0.08206 liters atmospheres mole Kelvin. And our temperature is 473 Kelvin. Our units of atmospheres cancels out, liters cancels out, and Kelvin cancels out to give us 0.00185 mole. So that equals N. So you see we have grams here. So now all we have to do is solve for the molecular mass, molar mass. So 0.145 grams divided by 0.00185 mole gives us 78.4 grams per mole. And that is of our molecular formula. So remember up here, we're going to take our molecular formula of our molecular weight of our molecular formula, which is, we just solved for it, 78.4 grams per mole. And we're going to divide it by our molecular weight of our empirical formula. So that would be carbon is 12 and hydrogen is 1. So that would be 13.019 gram per mole. And when you do that, that's going to give you a number 6. And that 6 is what you're going to multiply the subscripts in your empirical formula to give you C6H6. That is actually benzene. Okay, so this equation, we have an equation, and this should be 2NO2, nitrogen dioxide. So that's a little subscript 2. Oxygen should be O2. So that should be a subscript. Sometimes it doesn't convert over with the different programs. Okay, so we have a balanced equation. Let's make sure it's balanced. We have 4 nitrogens. 2 nitrogens, 4 oxygens. Yeah, so it's balanced. That's good. If 9 liters of NO react with excess oxygen. Oh, I'm sorry, this is oxygen. So this is not a limiting reagent because we have excess. So we know we have 9 liters of NO. Are reacting with excess oxygen at STP. Okay, so we know we can use 22.4 liters equals 1 mole. We need that conversion. What is the volume in liters of NO2? So what's the volume? Well, here's a volume and here's moles. And so we can go from liters of NO to moles of NO using 22.4 liters equals 1 mole because we're at STP. And then from moles of NO, we can go to moles of NO2 on our product side. And then it's asking for volume, and we can go to volume of NO2 by using 22.4 liters equals 1 mole. So when you do this, you take your given, which what you're starting with, the amount, 9.0 liters of NO over 1, and then you use this conversion. You put liters on bottom, 22.4 liters for 1 mole of NO, nitrogen oxide, and then we can go from our mole to mole bridge. Mole of NO, we can change the substance to mole of NO2. And we do this by our coefficients. So if you look here, you have a 2 in front of NO, and you have a 2 in front of NO2. And now let's cancel these out, liter, mole of NO, mole of NO. We're at mole of NO2, it's asking for volume, and we can go from, for 1 mole of NO2, we have 22.4 liters. If you put this in the calculator, 9 divided by 22.4 times 2 divided by 2 times 22.4, you will get 9.0 liters of NO2 as your answer. Okay, this problem has a mixture of gases containing 0.31 mole of methane, CH4, 0.25 mole of C2H6, and 0.29 mole of C3H8. Okay, so when you're given the moles, you should start thinking mole fraction. You should start thinking Dalton's partial pressure, Dalton's law of partial pressure. And you should start brainstorming some of these formulas you know, like PT equals PA plus PB plus PC, dot, dot, dot. So you can add all the different partial pressures of the different gases. That's one. And then if you want partial pressure of A, you can do mole fraction of A times the total pressure. Those are your formulas. And what is the mole fraction, which is A, would be the mole of A over your total mole. Okay, so obviously we can add up our total moles here. And if you add up the total moles, you'll get 0.85 mole. And so it gives us our total pressure. We're given PT, and we can, so we have PT and XA. So we can use this formula here to calculate the partial pressures of each of the gases. So the partial pressure of CH4, okay, so PT equals the mole fraction of CH4 times the partial pressure of CH4. And so it wants the partial pressure of CH4, so this would be P total divided by the mole fraction of CH4 is going to equal your partial pressure of CH4. And so how to get the partial pressure of CH4? Well, you just take the moles that belong to CH4, 0.31 mole, divided by your total moles, 0.85 mole, and that's going to give you 0.365. Those units cancel out, so this is unitless. And the pressure total was given to you here, 1.5. So, and let me see if I can, yeah, sorry about this. This should be partial pressure equals CH4 equals mole fraction times the total. And then basically you don't have to rearrange this equation. It would just be PCH4 equals. So we just plug it in. So we got the mole fraction of CH4 and you got your P total, which is 1.50 atmospheres. So when you plug these in, 0.365 times 1.50 atmospheres, you get partial pressure of CH4 is 0.55 atmospheres. Okay, you do the same thing with the other two. So the mole fraction of C2H6 would be 0.25 mole divided by your total moles, 0.85 mole. That should give you a unitless number of 0.294. And then you multiply this by the total pressure of 1.50, and you should get partial pressure of C2H6 would equal 0.44 atmospheres. Okay, you want to do the same thing with the last one. So the mole fraction of C3H8 is 0.29 mole divided by your total mole, 0.85 mole, to give you 0.341. And then your partial pressure of C3H8 would be 0.341 times your total pressure given to you in the problem, which is 1.50 atmospheres. You multiply these two together, you should get the answer. Partial pressure C3H8 is 0.51 atmospheres. Okay, so this problem, calculate the volume of carbon dioxide produced at 37 degrees and 1 atmospheres when 5.60 grams of glucose is used up in the reaction. So all these numbers here are little subscripts. This one is not, of course, and this one is not. Okay, so calculate the volume of CO2. So we're talking about here. So they want the volume of CO2. They give you, in the problem, a temperature, 37 degrees Celsius. Notice it's gas, so 273 Kelvin. That works out to be temperature of 310 Kelvin. Since it's gas, we can apply the PV equals nRT. Then we have 1 atmosphere, so we have pressure of 1.00 atmospheres. And we can figure out moles from we can figure out the moles from the moles of glucose. So we're going to go from grams of glucose to moles of glucose to moles of CO2. And we'll do the mole to mole bridge. So there's a 1 mole of glucose from the equation equals 6 moles of CO2. That's how we'll get moles. So we also have R, which is 0.08206 liters atmosphere mole Kelvin. And it wants the volume. So calculate the volume. And are we given pressure? Yes, pressure equals 1.00 atmospheres. So the first thing we're going to do is we're going to, we have our equation here, and we want to solve for volume. So we're going to go V equals nRT over P. So that's worth 2 points there by isolating our variable after we write our equation. And then we have to, we've already defined all our variables except for N. So now we've got to solve for N. We're going to use this plan. So we're going to take 5.60 grams of glucose, C6H12O6, and we've got to calculate the molar mass of glucose. I came up with 180 grams of glucose, C6H12O6, for 1 mole of glucose. And then looking at the coefficients, it's a 1 to 6 mole ratio. So for 1 mole of glucose, we have 6 moles of CO2. And so grams cancel out, moles of glucose cancel out to leave us moles of CO2. That's exactly what we need for N. And that works out to be 0.187 moles of CO2. So now we can plug everything in our formula for volume. So volume equals 0.187 moles times 0.08206 liters atmosphere mole Kelvin. Remember to write your units 310 Kelvin. You need to make sure the units cancel out, and your pressure is 1.00 atmospheres. When you cancel this out, moles cancel out, Kelvin cancels out, atmospheres cancels out, and we're left with liters, and that is just fine for volume. So that works out to be 4.76 liters. Okay, we didn't actually have the apparatus in here, but you've seen the apparatus. So you can imagine a big apparatus filled with helium at 1.2 liters and 0.63 atmospheres. And then we have this little one here of neon. actually it should be the other way around, right? Because we have 3.4 liters and we have 2.8 atmospheres. So that's our initial conditions. This is V1, this is P1, this is V1, this is P1. And the question is, calculate the partial pressures of helium and neon after the stopcock is open. Okay, so this is initial. And then once the stopcock is open, you have all the gas mixing together. Okay, and so now you have a new volume, volume 2. So you have to figure out what volume 2 is, and you just add these volumes together. So volume 2 is 1.2 liters plus 3.4 liters, and that's going to be 4.6 liters. And so what you have to do is you have to solve for P2 for helium, and you have to solve for P2 for neon. And then for your total pressure, it'd be P2 plus P2 of helium plus neon. And then so your partial pressure then would, you don't need total pressure, does it? It has to calculate the partial pressures. Okay, so you basically, you're just figuring out P2. All right, so you know your equation, P1 V1 equals P2 V2. You have to isolate your variable, P2 equals P1 V1 divided by V2. And so now you plug and chug. So your initial pressure for helium is 0.63 atmospheres. Your initial volume is 1.2 liters, and your new volume is 4.6 liters. And that works out to be partial pressure of helium, 0.164 atmospheres. And then you do the same for neon. So your formula then is P1 V1 divided by V2 equals P2 for neon, and you put in your initial pressure of 2.8 atmospheres times 3.4 liters divided by your new volume, 4.6 liters, and you put that in your calculator, and that should give you 2.07 atmospheres for the partial pressure of neon. This slide, we don't have anything, so their next question is about the kinetic molecular theory and talking about molecular speeds at different temperatures. So you will get questions about this. So you need to look at your relationships. I know that we've talked about this in class. You have some slides. There are also some stuff in your book, some graphs, and you also have had a quiz and an assignment on this. So basically you don't have to memorize formulas, but you do need to know that as you increase your temperature, your kinetic energy increases, and this is a direct proportion. So gases will travel. So we're talking about velocity here. Velocity is u. I think it's a matter of, or v, little v, meters per second. And so your velocity, your speed is going to increase. Now, the other concept is, what if you have, you hold constant the temperature? So we also have graphs where the constant's held temperature, the temperature is held constant, and you compare the different gases that have different molecular weights. And so when they have different molecular weights, what is an observation to notice that your velocity, so your speed at which the gases travel, will decrease as the molecular weight increases. So this would be an inversely proportional. Let's just take a look. On this slide, we don't have anything, but it's your greenhouse gases. So the plan is for you guys to have about 20 points of your exam. So basically, you're given a page. You need to answer the questions. You can look at your slides on Google. So that's a take-home, or Google, Moodle, and that's a take-home portion. So make sure that you write clearly and it's easy for me to grade, and you answer the questions, and then you're going to turn that in on Monday when you get your exam, and that is November 21st. So go ahead and get those 20 points. Good job, guys. Okay, so it looks like problems 15 and 16 and maybe even 17 didn't copy. So I will just work those problems here on this slide. So problem number 15, you want to use your formula. The heat equals mass. I do specific heat by little s, delta T. I think Sapling does it with a little c. So that's specific heat. Like I said, I will use S, and the units are joules, grams times degrees Celsius. And the question is asking for you to calculate specific heat and identify the substance. So obviously this is your formula, you get a point for that, and then you're going to have to isolate your variable. So specific heat is connected to mass and your delta T by multiplication. So you're going to need to divide that. So Q divided by mass times your change of temperature equals your specific heat. Let's define your variables from the equation. Your heat given off is negative 3,307 kilojoules, which you need to convert that to joules so you can get specific heat in joules. So that would be actually it is joules. So that's joules. Okay. And then your initial temperature, 77.0 degrees. Make sure you define each one of these for full points on the exam. Final temperature is 12 degrees Celsius. So your delta T, new formula, is TF minus TI. And so the delta T is going to be 12.0 degrees Celsius minus 77.0 degrees Celsius, which ends up being a negative 65 degrees Celsius. Okay, so we have the Q, and then the mass is given to you 366 grams. So it's cooling down, and then you solve for specific heat. So you got 3307 negative joules divided by 366 grams times a negative 65 degrees Celsius. These are going to cancel out the negatives to give you a positive 0.139 joules grams degrees Celsius. If you look on tables, you can find that 1.40 joules grams degrees Celsius is mercury. Okay, that's problem 15. Now for problem number 16, the heat released kilojoules per mole of aluminum. Okay, so you're given your equation, 2 aluminum solid plus iron 2 oxide solid goes to aluminum 2 oxide solid plus 2 iron liquid. Now also in the problem they give you delta H, a formation of iron liquid is 12.40 kilojoules per mole. So you have to write down your formula, which is delta H of reaction equals the summation of your moles of your product of delta H of products minus summation of formation, delta H of formation of your reactants. So some way I know that you know that formula, and then you basically have to fill them in. So your products are here, and you need to look those up on a table or the back of the book for the delta H of formation. Since you're given, so you have 2 times 12.40 kilojoules per mole plus negative 1676 kilojoules per mole. And that's your products. Now you're going to minus your reactants. Aluminum will be 0 kilojoules per mole, and iron oxide be negative 826 kilojoules per mole when you look this up. So then you can write 0 plus and negative 826 kilojoules per mole. And then when you do your math, so you do 2 times this number minus this number because of the minus sign here, minus a minus. So that ends up looking like this, 24.8 kilojoules per mole minus 1676 kilojoules per mole plus 826 kilojoules per mole. And your delta H of reaction then ends up being negative 825.2 kilojoules per mole. Is that endothermic or exothermic? That's right, that's exothermic. Now the problem asks you though for kilojoules per gram of aluminum. So now you see that you have, that's for 2 moles of aluminum. So you do negative 825.2 kilojoules per per 2 moles of aluminum. Do the 2 because of the 2. And what's the molar mass? Grams per mole. You look at the periodic table, and for 1 mole of aluminum, you have 26.98 grams of aluminum. And so your moles of aluminum cancel out, and you're left with kilojoules per gram of aluminum, and that works out to be a negative 15.3 kilojoules per gram. Okay, so using your calculated delta H of reaction in problem 17, how much heat, so we're going to use this one, negative 825.2 kilojoules per mole. How much heat is released? Let's rewrite our reaction here. Our 2 aluminum, because we'll need those coefficients, plus iron 2 oxide, actually iron 3 oxide, goes to aluminum oxide plus 2 iron liquid. And that's your delta H. A lot of times you would actually just see this written as kilojoules. Kilojoules. That's your delta H for that reaction. Okay, now the question is, how much heat is released when 2.35 grams of aluminum reacts with 1.80 grams of aluminum 3 oxide? So since we have the amounts of both reagents, this is a limiting reagent problem. So we have to go from grams to moles. So we're going to go from grams of aluminum to moles, and just pick it. Just pick one. Moles of aluminum 203. I just picked that one because it's the first one. And then, well, you have to go to moles of aluminum, and then you can change the substance to moles of aluminum 203. And then you're going to do the same thing here. You're going to go grams of iron 203 to moles of iron 203 to moles of aluminum 203. Then we're going to choose the least. Moles of aluminum 203 will be our limiting reagent. And then we will use the limiting reagent moles, and we'll just use the moles of aluminum 203, and we'll use this whole negative 825.2 kilojoules equals 1 mole of aluminum 203 to figure out the amount of heat. Okay, the amount of H, enthalpy. So let's do exactly that. You will see something like this on the exam, so be prepared to do that. Okay, I think you'll have formula weights given to you. Okay, so let's just start. 2.35 grams of aluminum. I look at the periodic table, I see 26.98 grams of aluminum for 1 mole of aluminum. And I know from this equation for 2 moles of aluminum, we have 1 mole of aluminum 203. And when I plug that in my calculator, I get 0.0436 moles of Al2O3. And then I'm going to do the next one, 1.80 grams of Fe2O3. Put that over 1. I'm going to look at the periodic table. I'm going to add 2 irons, 3 oxygens. I'm going to get 159.7 grams of Fe2O3 for 1 mole of Fe2O3. And I'm going to look at my equation, and I'm going to see that for 1 mole of Fe2O3, we have 1 mole of Al2O3. And when I put that in my calculator, divide, I get 0.01127 moles of aluminum 203. So now, which one's the least number, 0.4 or 0.1? That's right, 0.1. So my limiting reagent would be iron oxide. Now I'm just going to use that amount, that answer, 0.01127 mole of aluminum 203 over 1. I'm going to use my delta H. For 1 mole of aluminum 203, I have negative 825.2 kilojoules of heat. And that works out to be negative 9.30 kilojoules. So 9.30 kilojoules of heat is evolved. Okay, using Hess's law, so we want to calculate the enthalpy for methane, CH4. So here's our equation here at the bottom, and we want to figure out what the delta H, or reaction, would be for this equation. So we're just going to use these equations to do this, and you will get something like this also on your exam. So first thing we're going to do is we're going to find carbon. And I go up here and I see carbon. Okay, and it's on the reactant side and it has the right coefficient. So I'm fine. I'm going to go to the next. So now I have to find 2 hydrogen. Okay, I find 2 hydrogen. It's on the correct side of the equation, but it needs a 2 to run through. So I'm going to rewrite that equation. 2H2 plus 2 times 1/2 is 1. So 1 oxygen goes to 2 H2O, and then I also have to do that to the delta H. So negative 286 kilojoules times 2. So now I'm going to mark that out so I don't use it again because I rewrote it here. And I'm going to box this in. Okay, so we're there. We're good. We've got these 2 boxed in, and now we have methane, CH4. Well, my first equation has carbon dioxide. My second equation has water. And my last equation does have methane, but it's on the wrong side of the equation. I need it on the product side. So I'm going to rewrite this one, and I'll flip it. So CO2 plus 2 waters goes to CH4 plus 2 oxygens. And I've got to change the sign of the delta H to now a positive 892 kilojoules. And I'm going to X this equation out now. So I use this one, and I'm going to box in my CH4. Now I want to make sure that all the other elements cancel out. So we have oxygen on the reactant side. We're going to add all these up. I'll tell you what, I'll just go ahead and rewrite this one too. Plus O2 goes to CO2, delta H equals negative 393 kilojoules. Okay, so I put that down there. Now we're going to add all these up. So carbon's good, plus 2H2 is good, plus, well, that's it. Okay, so now I'm going to see we have 1 oxygen, 2 oxygens. So we have 2 oxygens, and we can go ahead. We have a CO2, and we have 2 waters. And then it goes to, on our product side, we have CH4, and we also have a CO2 over here. We have 2 waters, and we have 2 oxygens. You notice they're on both sides of the equation, so we can cancel those out. We can cancel out the waters and the CO2. So there's our oxygens canceled out, our CO2's canceled out, and our waters canceled out to give us this overall equation. So since everything canceled out, it worked out, and now we're going to calculate our overall delta H for reaction. So I'm going to say negative 393 kilojoules plus a negative 286 times 2 kilojoules plus an 892 kilojoules. And when I add that up in my calculator, I get a negative 136 kilojoules is my answer.